This video is for Unit 6, Lesson 4. We've started to look at properties of exponents. There's two that we've seen so far. Those two are if you have x to the a times x to the b, you can combine those by keeping your base the same and adding your exponents. So that was the first rule. The second rule we saw was if you have x to the a raised to the b power, you can keep the base the same and multiply the exponents. That's the power to a power rule. So we've got a rule for when we're multiplying. We've got a rule when we raise something to a power. Today, we're going to work on what we can do with exponents when we are dividing. So there's an important idea about fractions that I just want to remind you of, and that's the following. In part A here, if you have 7 divided by 7, the answer to that is 1. 5 squared over 5 squared. 5 squared is 25. So the top and bottom of this fraction is 25, and 25 over 25 is also 1. N over n, also 1. 10x to the third over 10x to the third also equals 1. So anytime you divide an expression by itself, the answer is going to be 1. So we're going to use that to help us with simplifying fractions. And for this next part, it's important that you look at each piece of this and follow along with it, because what we do with numbers, you know a lot of shortcuts for how to reduce fractions, but the actual process for reducing a fraction when we have numbers is going to be the same when we have variables. But it's not as easy to take the shortcuts when you have variables. So way back when you were first taught to reduce fractions, you were told to look for a greatest common factor, also known as a divisor, of your numerator and denominator. So if I think about numbers that I can divide into 18 and into 30, 18 can be divided by 1 in itself, 2 and 9, 3 and 6, and that's it. 30 can be divided by 1 in itself, 2 and 15, 3 and 10, and 5 and 6. So if I look at the largest number that can be divided into both of those, I see that it is 6. The second thing you were taught to do was to rewrite 18 over 30 in equivalent form. And we're going to rewrite it using the GCF from part A. So 18 can be rewritten as 6 times 3, and 30 can be rewritten as 6 times 5. So this fraction that I wrote using products is equivalent to what we started with. The last part of simplifying, when you rewrite a fraction using a product, you can break that apart. So I can say that that's the same as 6 over 6 times 3 over 5. And the reason for that is, remember, when you multiply fractions, you multiply straight across. So 6 times 3 would give you the 6 times 3 in the numerator, and the denominators of 6 times 5 would give you 6 times 5 in the denominator. Now, what's nice about this is we know 6 over 6 is 1. So this can be simplified further into 1 times 3/5, which is just 3/5. So we know that 18 over 30 can be simplified and rewritten as 3/5. Now what we're going to do is we're going to simplify fractions that involve exponents in a similar manner. So we're going to figure out the greatest common factor of 2x to the 5th and 6x to the 3rd. Okay, so 2x to the 5th can be rewritten as 2 times 1 times x times x times x times x times x. 6x to the third, I'm going to break 6 down. 6 breaks into 3 and 2. So that can be rewritten as 3 times 2 times x times x times x. So the greatest common factor is what they share. So I notice they share a 2, each of them, and they each share 3 x's. So my GCF would be 2x to the third. So that's my first step. My second step is to simplify the fraction using the GCF. So my original fraction was 2x to the fifth over 6x to the third. But we decided that 2x to the third was a common factor to the numerator and the denominator, which means I should be able to write the numerator and denominator as 2x to the third times something else. 2x to the third. If I want to get 2x to the fifth, I'm going to need to multiply it by an x squared. 2x to the third times what would give me 6x to the third? Well, that would just be 3. So now I can rewrite this. I can break this product apart. 2x to the third over 2x to the third times x squared over 3. This becomes 1, and 1 times x squared over 3 is just x squared over 3. So the fraction 2x to the fifth over 6x to the third can be reduced and rewritten as x squared over 3. So we should be able to do this using, we should be able to simplify almost any expression with monomials using this technique, but the practice is really important. So let's go ahead and look at part A. As we go through this, you're going to start to notice some patterns and maybe some shortcuts. Okay. If you start to notice some shortcuts, you can try to use them. But if you find that they don't work, try to think about why. If you don't understand why, ask and we can talk about it. So for part A, I've got x to the sixth over x squared. What's the largest thing, the largest factor of both of those? Well, x to the sixth is 6 x's. X squared is 2 x's. So what do they have in common? It would be x squared. So the first thing I'm going to do is I'm going to rewrite my numerator and my denominator as x squared times something. Well, remember when we multiply, we add the exponents. So in my numerator, I'm going to need an x to the fourth. The denominator is x squared, so I'm just going to keep it 1. X squared over x squared is 1. So x to the sixth over x squared simplifies to x to the fourth over 1. You could also write that just as x to the fourth. Okay, part B. What can I divide a 10 and a 2 by? I think the only thing that goes evenly into both of those is a 2. There's 9 m's in the top and 4 m's in the bottom. So how many do they have in common? Just 4. So I'm going to rewrite this as 2m to the fourth times something over 2m to the fourth times something. In my numerator, 2 times 5 will give me 10. M to the fourth times m to the fifth will give me m to the ninth. And in my denominator, it's just going to be 2m to the fourth times 1. These divide out and become 1. So my answer is 5m to the fifth over 1, or just 5m to the fifth. Let's look at part C. I've got a 6 and a 4. So if I think about the largest number that can divide evenly into a 6 and a 4, that's a 2. My numerator has 3 y's. My denominator has 7. So the number they have in common is 3. If you want to pause the video and try to write the top and the bottom as a product using 2y to the third, you are more than welcome to. If you'd like to keep watching, follow along, you are also welcome to do that. So I'm going to rewrite the top and the bottom with 2y to the third. In my numerator, what's missing is I need to get that 6. So I'm going to multiply by 3. In the denominator, I need to get a 4, so I need to multiply by 2, but I also don't have enough y's. How many more y's do I need? Well, I need 4 more of them to get 7. The common factor of 2y to the third divides out, and my answer is 3 over 2y to the fourth. Okay, last one, part D. If I think about what can divide evenly into 4 and 12, it can be 2, but it also can be 4. So my greatest common factor is 4. And then how many x's do they share or have in common? It's just x to the third. So my numerator is going to be 4x to the third times 1. My denominator is going to be 4x to the third times 4 times 3 is 12. And then I need 5 more x's so that I have 8 multiplied together. These divide out. So this fraction simplifies to 1 over 3x to the 5th power. So if you take your time, it will help with this. Now, some of you may have already noticed this pattern, but we're going to take a look at this. We're going to simplify each of these. So we're just working with variables right now. So for letter A, if I think about what my GCF is, how many x's do they have in common? Well, they share 3. So my numerator can be written as x to the third times x to the 7th. And my denominator can be x to the third. These are going to cancel out. So my answer is x to the 7th. You could also write it as x to the 7th over 1. Now, why would it make sense that I would have x's left in the numerator? Well, if you think about x to the 10th, there's more x's in the top. So 3 of the x's from the bottom are going to cancel with 3 of the x's in the top. And where will I have x's left? I'll have x's left in the top. And how many will there be? There will be 7 left after I cancel them out. So for part B, if I look at this, where do I have more n's in the top or the bottom? Well, I've got 12 n's in the top and 8 in the bottom. 8 in the bottom will cancel with 8 in the top. And that's going to leave me with 4 left over in the top. So the answer to this is n to the 4th. And it makes sense that it would be n to the 4th over 1 because there's more n's in the top. Now, what happens when my larger number of variables is in the bottom? I'm still going to have y's cancel, okay? The 3 y's in the top will cancel with 3 of the y's in the bottom, but where will I have y's left over? There's going to be y's left over in the bottom. And whenever you've got values in the denominator, the way you show that is by putting 1 over y to the 6th. So in letter D, same thing. Where am I going to have t's left over? Well, there's more in the bottom. So the numerator is going to divide out to 1. How many extra t's will I have left in the bottom when the 2 from the top cancel with 2 from the bottom? There'll just be 3. So this leads us to a shortcut that can be helpful. When the power in the numerator is greater than the power in the denominator, so this is the bigger one, your answer is going to be x to the a minus b. So you're going to have more x's left in the top. You could also write that over 1. Okay. And how do you know how many are going to be left? You just subtract the exponents. When the power in the numerator is less than the power in the denominator, so when you have more in the bottom, The numerator is going to become a 1. And how many are left in the bottom is going to be just the difference between the bottom and the top. So that's a quick little shortcut, but you can always go back to finding the GCF and rewriting it. That method will always work. So let's look at these using the patterns. So if I look at A, where do I have more X's? Well, I've got more X's in the top. So I'm going to end up with X's left in the top. The difference between 8 and 5 is 3. So my answer would be X to the third over 1 or just X to the third. For B, where do I have more Y's left over? Well, there's more Y's in the bottom. How many more? There's 2 more. And the numerator has to be 1. I cannot write this as Y squared. That is not the same thing. So if you've got 1's left in the bottom, it has to be 1 over. Part C is a little bit tricky, okay? I'm going to show you the shortcut, but you can always go back to using the GCF. I know that for my numbers, I'm dividing 8 by 12. So I'm going to do that using my calculator. 8 divided by 12, and that reduces to 2 over 3. Now the question is, where will you have T's left over? Well, there's more in the top. So I'm going to have T's left over in the top. How many? Just 3. So this is one way you could write the answer. The other way you might see it is 2/3 T to the third. Okay, so I want you to see both ways. Let's do part D. So in part D, and I'll go ahead and write my answer down here, 15 divided by 3, hopefully you know that that is 5. And as a fraction, that would be 5 over 1. Then let's look at the R's. Where do I have more R's? Well, there's more in the bottom. How many more? 4. So it would be 5 over 1 R to the 4th. Another way you could see that written is 5 over R to the 4th. Again, if you get stuck, go back to the idea. Your GCF in D is going to be 3R. So I can rewrite my numerator as 3R times 5, and my denominator is 3R times R to the 4th. Those cancel, and there's your answer. So if you're stuck and you don't want to use the shortcut, you can always go back to writing the fraction as a product. Okay, that's the end of this video. You can go on and do the practice.